All right, so last week we talked about the three gas laws. We talked about Boyle's, Charles, and Guy-Lussac's laws, right? And those were all involved pressure, volume, temperature, and not only that, but it was like we had initial conditions and then something happened and they changed, so then we were able to solve for initial and final. That was the whole point of those gas laws, right? And then we had the combined gas law where we stuck them all together, correct? All right, so now we're going to learn about a fourth, it's really the fifth, but we're going to talk about the ideal gas law today. So first of all, the ideal gas law uses this equation, and there's a mnemonic device that says Pivnert to kind of help you remember what it is, but PV equals nRT. I feel like it's easy to remember. I don't know why, it kind of flows. PV equals nRT. But really quick, just to kind of show you how we get to the ideal gas law, because basically, last week we learned about the combined gas law. Does anybody remember what the combined gas law is? Alright, I probably need to change the color. That's too red. Okay, so PV over T, right, equals PV over T. This is the combined gas law we talked about last week. Does anybody remember when we talked about Avogadro's law for just a second and it involved moles? Anybody remember where we put moles? Bottom. Moles went on the bottom. So we could add moles to this, and we get, on the initial conditions, PV divided by moles times temperature. The final conditions, PV equal or divided by moles times temperature, and they should be a ratio. But the ideal gas law kind of says, well, we didn't really care about before and after. We need some sort of equation in which we can find the information of a gas right then and there. And so what they did is they kind of took like 1/2 of this and then set it equal to some rate. And what they found is if pressure is at 1 atmosphere and temperature is at, does anyone remember what standard temperature and pressure is? 0 degrees Celsius, which is 273 Kelvin. So here we have our STP, we have standard temperature and pressure. So under these conditions, when you're at standard pressure, you're at standard temperature, okay? And then if we also take into account 1 mole has what kind of volume? 22.4. 22.4 liters. If we take into account at standard temperature and pressure and how these two numbers relate, if we take these two things into account and plug them all into the combined gas law, we're going to get this rate. It doesn't matter what gas we're talking about under standard temperature and pressure, and and if you have 1 mole, they all are going to give you the exact same rate. So this is why we call it the ideal gas law. Okay, now is every gas going to be ideal all of the time? No, but when they are in these ideal conditions, they all are going to behave identically and they all are going to be equal to some rate. Yes?
So each gas is going to have the same rate?
No, every gas under ideal conditions is equal to the same R. So it doesn't matter. As long as you're at these conditions, the rate. So basically what we're going to do is we're going to, when we're using the ideal gas law, we're pretending the R is taking that fact that if we were at perfect conditions, it would have this rate. So when we use R, it allows us to not be at perfect conditions anymore, because it's going to factor in all of the perfect condition factors.
Oh, so it's like you're going to use this and you're going to use it.
No, we're going to use PV equals nRT, but that's how we get PV equals nRT, because under standard conditions, all of this is going to be equal to R. So now that we know what R is equal to, we can use it in that equation, the PV equals nRT. R is our constant. Because, do you think pressure is always going to be 1 atmosphere? Do you think temperature is always going to be 273? No. But because we know what R is equal to, because R is a constant, we can now use other factors. Okay? All right, so in your notes, we have a couple of blanks. I just talked about them, but let's go through them just to make sure we all write them down. Standard conditions, again, is 1 atmosphere and 0 degrees Celsius. I want you to go ahead and write down 273 Kelvin, and for some reason part of my slide isn't showing up right here. But on my computer, you can see N equals 1 mole, too, right next to standard conditions. So standard conditions is 1 atmosphere, 0 degrees Celsius, and 1 mole, even though it's not showing up for some reason. R is your ideal gas law constant. R is equal to, I'm just going to exit and try this again, see if it'll fix itself. There we go. Okay, so R is equal to 0.08206 liters times atmospheres divided by moles times Kelvin. Now, why do you think it's so important that we keep track of our units when you're using the ideal gas law? It has to be in kelvins. It has to be in liters. It has to be in atmospheres. It has to be in moles. Usually, we're going to talk about density here in a little bit. Density is usually given in milliliters, so we would have to do a little bit of converting. You have to watch your units when you're using the ideal gas law, or you'll make a little mistake somewhere, okay? Because there's a lot of converting. Now, as you guys can see over on your paper, over to the right, what did I put in there for you?
Oh, using the National Armed Society.
It's in the folder already. Okay, so if you guys notice over to the right side, what do I have on your paper for you? Different units of R, right? Because sometimes you're given in torrs. So instead of converting, maybe you could just use this R. Or you can always convert. That way you only have to remember one R. But if you're ever in the need for a different R with different units, I've given you 1, 2, 3, 4, 5 different ones. So sometimes there's even the second R is for joules, so that's when we're talking about energy. If you notice, the moles and the Kelvin always stays the same. It's the top that's changing. So if you're ever looking for a different R, there you go. We're going to always use the standard one for today. But if you're looking, when you're doing your practice problems, if you need a different R, there they are. Okay, so when do you use PV equals nRT? Well, the ideal gas law describes the conditions of a gas now. Okay, so if you remember, last week when we talked about the other gas laws, we were talking about when something was changing. So we had initial conditions versus final conditions. Okay, well, PV equals nRT is when you're wanting to know how the gas is behaving right now. So if usually if you see two sets of variables, if you see pressure twice, if you see volume twice, if you see temperature twice, that should be a signal that we're not using the ideal gas law, that you need to be using one of those other laws, maybe the combined gas law or Charles or Boyle's or Gay-Lussac's. But that's kind of, I actually have one in one of the examples today to see if I can keep you guys on your toes, to see if we can catch when we're supposed to use the PV equals nRT and when we're not. So be ready for that. Okay, so wait just a second. You guys get caught. Okay, then we're getting ready to start where it says ideal gases in just a second. All right, so R, the gas constant. There's the main one that we're going to use, and here's the others that are on your page. Again, for the most part, if you notice, the denominator is always moles times Kelvin. The only thing that's changing is honestly your unit for pressure, and then not only that, but we threw in 2 units for energy, so we have joules and calories up there. But for the most part, we're going to be using the other one, but just in case, there's the other. Okay, so ideal gases are honestly a hypothetical substance. Do you think anything is ever going to behave always at 1 atmosphere, always at 273 Kelvin, always 1 mole, always 22.4 liters? Probably not. So it's kind of a hypothetical ideal, but the ideal gas whose pressure, volume, and temperature is completely described by the equation. So honestly, when we're talking about these types of gases, almost you need to think of it as a limit. As gases approach ideal behavior at low pressure and very, very high temperatures. So at low temperatures and high pressures, it's kind of like a nice, pretty sunny day, okay? Because we talked about pressure and we said that Low pressure is actually bad weather, so I retract my example I was just about to go. But anyhow, it's kind of like a limit. Think about if this were to happen, it would be okay, maybe my example will work. How often do we have really, really, really bad hurricanes?
Never.
Maybe once every 3 or 4 years, right? Okay, that's how likely it is for us to get to perfect ideal gas conditions. Okay, that's not going to happen very often because low pressure is not the norm. High temperature is not the norm. Around here, we kind of like to stay in the medium pressure and we like to stay in the medium temperature range. We don't like the extreme in either direction. Okay? Even though gases are not necessarily ideal, we use the laws anyhow, and unless told to do otherwise because they give us good estimates. Because if we were able to get under these perfect conditions, we could use R. So again, R allows us to not be under perfect conditions because it gives us a way to factor in perfect conditions in unperfect conditions. All right, so you guys just ready to do an example? All right. So again, at this point, you guys know how good you are at math. You know what you need to do. If you need to list your variables, list your variables. If you like to underline and circle, if you like to underline and circle, underline and circle. I don't really care what process you do anymore, but when you're using the ideal gas law, you need to check what? What do you need to constantly be checking? You need to constantly be checking your units so that it'll match our R factor. So honestly, what I like to do is I just like to write my equation down, and then I like to write my equation down, and then I like to plug things in. So we have a 47.3 liter container containing 1.62 moles of helium, and it is heated until the pressure reaches 1.85 atmospheres. What is the temperature? Well, that was nice the first go around. We are in atmospheres, we're in liters, we are in moles, no converting necessary. Probably not going to be that way anymore. But for the first go around, let's just plug in. So our pressure is 1.85 atmospheres. Our volume is 47.3 liters. Set that equal to our moles, which is 1.62. And of course I ran out of room, so I'm going to have to continue. Does anyone remember what R is off the top of your head? 0.082. Well, let's round to 1. Let's just use 3. Okay, does anyone remember what the units were? Atmospheres, liters over moles. Okay, whew, that was rough. And then we have to, again, multiply that by our temperature, which is what we're solving for. Okay, then we have to do some algebra, which is why I wanted you guys to get out a calculator so that me just giving you the right answer, sometimes I don't think we don't make a practice at putting these in the calculator. So I want you to actually take a second, put this in your calculator, let me know what you get. What are we getting? Okay, we get 657.9, right? How many significant figures do we get to keep? 3, so we're going to round that to 658. And what's our unit going to be? Kelvin. How do we know which R to use? Well, our pressure was in atmospheres, honestly. So look at the pressure that you're given, and then that's what R you know to use. Because the other R's have a different unit for pressure. Okay. All right, so 658 Kelvin. Not too bad, again, just algebra. No more stoichiometry, limiting factors, all of that fun stuff. Although we are going to do something with empirical and molecular formulas here in just a second. But this part, just algebra, right? So let's do example number 2. Example number 2 says krypton gas is, krypton gas in a 18.5 liter cylinder exerts a pressure of 8.61 atmospheres at 24.8 degrees Celsius. What is the mass of krypton? We see Celsius. We know that we have to be in Kelvin. So before I even start, I'm just going to go ahead, or I probably should turn on my writing. I'm going to go ahead and add 273 to this, and I'm going to get, I can't remember. Wow. 297.8, sorry. Sometimes when I do math in my head, it's not a good idea. So now I'm going to do the exact same thing. I like to just plug into a formula. If you guys like to list your variables, again, do whatever works for you. So PV equals nRT. Okay, we're wanting to know mass. We want to see a problem. Is this a one-step process? What are we going to have to do first? We need to find moles, and then we can convert to the mass using molar mass, right? So my pressure is 8.61 atmospheres. My volume is 18.5 liters. Set that equal to N. My R is the same as before because we're in atmospheres and liters. And our temperature is 297.8 Kelvin. And I didn't put my units for R because I ran out of room, but they are 8 atmospheres, liters over moles, Kelvin. Okay, do some algebra skills. We're going to solve for N. I'll do this one for you guys. N should be in the realm of, how many significant figures do I get to keep? 3, so I'm going to round it to 6.51 moles. What do you think I should do now? Convert to using molar mass. So where am I going to get my molar mass? Periodic table. 1 mole of krypton is what? 83.80. So moles cancels. We're left with grams. So we should be getting in the ballpark of 545.66, so on and so forth. We can only have 3 significant figures, so we are going to round this to 546 grams. So if we are doing this in a lab type setting, we are going to have, or we're going to need 546 grams of this gas in order to get these types of results. All right, so one more example. Let's start reading example 3. It says a sample of gas has a volume of 4.18 liters at 29 degrees Celsius and 732 torrs. What would its volume be at 24.8 degrees Celsius and 756 torrs? What do you think we're going to do? Well, we do need to change to Kelvin, but what else? Anyone else see a problem? Do we need to change from torrs to atmospheres? It starts in torrs, it ends in torrs. What else? Are we using PV equals nRT? No, what do you think we should use instead? Nope. Because we have all 3 variables. So we need to be using the combined gas law because we're dealing with all 3 variables. None of them are staying consistent, right? Our pressure changed, our temperature changed, and we're wanting to solve for our second volume. So nothing's staying consistent. All 3 of the variables are changing, so we need to use the combined gas law, which is PV over T equals PV over T. So this and this and this go together, and then this number and this number go together, right? So my pressure, 732. My volume, 4.18. My temperature is 24.8 plus 207, or 29 plus 273. which is 302. My second pressure, 756, times my volume, which is what we're solving for. Divide that by 24.8 plus 273. 297.3. And we can cross multiply. We can solve for our volume, whichever you guys prefer to do. But by the time you do all that algebra, first of all, how many significant figures do we get to keep when all is said and done? 2. Why do we only get to keep 2? Because of our 29 degrees Celsius, it only has 2 significant figures, so we are going to get 3.99101 in our calculator. So it's going to be 4.0, and what's my unit going to be? Liters. So just because we know about the ideal gas law doesn't mean we're always going to be using this. This is a perfect example. Right off the bat, we knew not to use PV equals nRT because our conditions were changing. As soon as you see that they're changing for some reason, other gas laws. Yes?
So on the test, are you going to give us all of the equations? Like not test with the but like give it to us? Or
I'll probably give you like the combined gas law and this one because the combined gas law involves all of the other ones. But I probably won't give you PV equals PV and P over T equals P over T. I probably won't give you those, and I'll probably ask you to tell me which one's which. But I'll give you the combined gas law and this one.
what about like the value of R?
I'll give you the value. I'm not going to make you memorize that. I'll give you that one. All right, so the next thing that we're going to talk about is density and molar mass, maybe. Density and molar mass. So the density of gases can be determined in a roundabout way. So first of all, you're not going to have enough room to write this because that's a really tiny space, but we'll be fine. So first of all, how do we find density?
Volume divided by
Density is mass divided by volume, correct? Well, we can kind of, now that we know what volume is equal to using PV equals nRT, let's just do a little bit of substitution. So PV equals nRT. So what can I do to get volume all by itself? I can put P on the other side. So now I know that volume is equal to nRT over P, correct? So what I'm going to do is I'm going to shove this down here so that I can solve for the density of a gas. So I can see that density is equal to mass divided by nRT over P. And we know something about a fraction and a fraction. What do we know about a fraction and a fraction? This P is no longer in the bottom anymore. When you multiply by the reciprocal, where does it go? It goes to the top. So then we get this new equation, right? The mass times our pressure divided by N, which is moles, times R times T is going to give us the density of a gas. But just when you think we're done, we know something. What is this right here? Let me change the color. Let's look at this mass and the N. We know something a little bit about mass divided by N. So we have grams divided by moles. So that is our molar mass, right? So that is honestly, when I look at this equation, M and N are going to be the hard things to solve for, but that ends up not being the hard thing at all. Why? We can look up the molar mass on the periodic table. So grams per mole. All we're doing there is the molar mass, so we can actually rewrite it one more time. And I'm going to give it a funky M so we can tell a little bit. So if you take your molar mass times by your pressure divided by the R, which is a constant temperature, it makes this equation much, much, much easier. There's not very many variables we actually have to deal with, is there? So there it is typed. Again, try to denote your molar mass M a little bit different from mass M, okay? Just so that you don't get them confused, and so that I always give the molar mass a curvy, cursive looking. Okay, so the higher the pressure and the molar mass, the more dense the gas, which makes sense because if you think about a container, what's going to happen in here if the container stays the same but the pressure is increasing? What's going to happen? It's going to get more and more and more dense because you guys are going to start feeling like you're under a lot of pressure. Your ears are going to start wanting to pop and vice versa, okay? All right, so to determine the molar mass of a gas, we can rearrange it. Basically, that's the same density equation I just did. I just rearranged it so that you're solving for molar mass. Even though sometimes we can look it up on the periodic table, but where this equation comes in handy is if you have an unknown gas. So you could, if you have an unknown gas, but you know the temperature it's under, you know what the density is, you know what the pressure is, you can solve for molar mass, and then you can turn around and look at the periodic table and you can identify the gas. So this last equation comes in handy when you're trying to identify something that you don't know, which we do a lot in here. All right, so let's do an example of this type of problem. So example number 4 says, what is the density of ammonia at 23 degrees Celsius and 735 torrs? First of all, I was mean. You're in Celsius and torrs, so we need to do a little bit of converting before we can even do anything. But first of all, what in the world is ammonia? NH3. NH4 is ammonium. Ammonia is NH3. So NH3. So now, let's just go ahead. We're going to add 273 to our degrees Celsius. So we're going to get 296. 735 torrs is no good either. We need to convert that probably to atmospheres. Is that what you said? Yeah, ATM. So does anyone remember the conversion factor from atmospheres to torrs? 760 torrs is equal to 1 atmosphere. So if you do 735 divided by 760, you get 0.967 atmospheres. And I kept 3 significant figures because 735 had 3 significant figures. We'll adjust for the temperature significant figures later on. Okay. So it's asking for density. What equation for density should we use? Which M? What kind of M? Molar mass M. So we're going to use molar mass M times P over R T. Did it give me molar mass in my equation? We know what ammonia is. We can have a periodic table. We can look up the molar mass. So nitrogen is 14. Hydrogen is 1, but we have 3 of them. So 14, 15, 16, 17. So the molar mass of ammonia is going to be 17.04, I think technically. Yeah, 0.04 grams per mole, and I ran out of room a little bit. So plug that in. So we're going to have 17.04 grams per mole. Okay, my pressure, 0.967 atmospheres. Divide that by my rate. What rate do you think I should use? We're in atmospheres and Kelvin. 0.0821. And I'm going to plug in my units just so that we can make sure everything cancels out this time around. So we're going to have atmospheres, liters divided by moles, Kelvin, and then finally we need to plug in our temperature, which is 296 Kelvin. Whew. Keeping track of all of these units is giving me a headache, right? All right, so I'm going to change my color so that we can see this a little bit better. So let's make sure all of my units cancel out. Let's see what we're left, because density we know should be grams per liter, grams over volume of some sort. So let's see what happens. So that mass, this atmosphere cancels out that atmosphere. This Kelvin cancels out that Kelvin. This moles cancels out that moles, correct? And we are left with grams divided by liters. So are we on the right track? Did we use all the right units? Yes. Yes, Monica? All right, so now we just get to do the fun math. We get to put all this in our calculator. How many significant figures do I get to keep? 2. So I am going to round my answer to 0.68 grams per liter. Now, we can completely leave this just like this because are we in density? Does anyone see a problem though? Why would we maybe not want to leave them in these units? That's not the standard unit for density. So if I were to go look this up to try to determine what gas I have, I wouldn't be able to. Does anyone know what the standard unit is for density? It's grams per milliliter. So we need to convert the liters, which is really easy. Does anyone remember how to easily convert from liters to milliliters? We move the decimal 3 times, or you can just add 0.68 times 10 to the negative third grams per milliliter. Okay, that's the easiest way. You don't have to remember which way to move the decimal. You could move the decimal, so technically you could do 0.00068 grams per milliliter if you really wanted to. I don't really care. You don't have to convert it at all. But our volume's on the bottom. So we're not technically. Can I erase this? We'll just do it by hand. Let's stop trying to do things in our head. So somebody remember 0.68. In case I forget. 0.68 grams per liter, correct?
You're right.
And then 1 liter, 1,000 milliliters. So we're dividing by 1,000 because milliliters is on the denominator. It's not. We would have moved it the other direction if we would have been on the numerator, but it's actually going to be getting smaller because milliliters is. Does that make sense?
Yeah.
Whenever things are in the denominator, it always kind of throws a wrench in things. So then that'll give us 0.12368 grams per milliliters. Or 6.8 times 10 to the negative fourth, or however of various ways you would like to write it, go for it. I'm pretty lenient. Okay, are we ready for the hard one? Yes. Yeah, you could have left the torrs alone. You could have used a different R value. I always use that one because I haven't memorized it. I don't have to bother with looking anything up. All right, so example 4. We just did. Example 5. There we go. Okay, example 5 says a compound has the empirical formula. My computer's just kind of has a mind of its own lately. Okay. A compound has the empirical formula CHCl, a 256 milliliter flask at 100 degrees Celsius and 750 torr, contains 0.8 grams of the gaseous compound. What is the molecular formula? Uh-oh. Let's go back to stoichiometry land. Let's go back to limiting factors. Let's go back to all of that 2 or 3 units ago, and let's try to remember what in the world the difference is between empirical formula and molecular formula. Yes? The empirical formula is the smallest ratio. So the ratio of carbon to hydrogen to chlorine is 1 to 1 to 1. But we all know that covalent compounds don't always follow the smallest ratio. And maybe it's 2 to 2 to 2, and maybe it's 3 to 3 to 3, and maybe it's 4 to 4 to 4. We don't know. That's actually what we're going to do a little bit of math right now to figure out. Now, no, we're not doing stoichiometry. No, we're not doing limiting factor, all of that stuff. We're going to be doing the density problems that we were just talking about, but the very last step, we're going to try to figure out what the molecular formula is. So let's just forget about empirical and molecular formula until we know the density. Once we know the density, then we can figure it all out. So right off the bat, we have milliliters, we have temperature, we have pressure, we have grams. What equation do you think we should be using? Not read my own handwriting. Is that bad? Okay, so in order to figure out the molecular formula, we need to know the molar mass. Because if we know what the molar mass is, we can determine if the empirical formula is the molecular formula and vice versa, right? So basically, we're going to be using the density equation, but we want to be solving for Just going to do a quick little do you guys want to see how I'm going to rearrange it? Or just want me to give you the equation? Okay. So basically, our molar mass is going to be equal to our mass times our rate times our temperature divided by our volume times our pressure. And again, I just did a little bit of substitution. I rearranged. I put density over on the right side. I put molar mass over on the left side because mass divided by volume is density, right? So I just switched two variables around. Everyone on the same page? It's not a new equation. I just rearranged it to make our math a little bit easier. So now all I'm going to do is plug in my variables. So I have 0.80 grams. I have my rate. I'm going to use the same one, even though we're in tours. I have that one memorized. I always use the exact same one. If you wanted Paula asked me a second ago if we could use a different rate. You can use a different rate if you want to. But I always use the same one because, again, I have it memorized. Our temperature is going to be 373 if you had to put that in a calculator. Scale. Our volume is 256 milliliters. Okay, and then our pressure. So we need to do a little bit of math on the pressure. What's the conversion factor for towards 2 atmospheres? 760. So I'm going to take 750 divided by 760, and I'm going to get 0.987. And that's in atmospheres. This is in Kelvin. This is in, if you guys remember, our 0.821 is in atmospheres times liters divided by moles times Kelvin. So again, let's make sure all our units cancel out before we try to do any of the math. This atmosphere cancels out this atmosphere. This Kelvin cancels out that Kelvin. Crap. Milliliters, liters. But easy fix, right? What do? Move the decimal 1, 2, 3 times. The milliliter goes away. So then that liter cancels out that liter. And we are in grams per mole. Is that what we want? Yes. So now we can plug all of this fun stuff into our calculator. And we should get an answer of, let's see here. What'd you get? Oh. We get 96.9779 grams per mole. How many significant figures do we get to keep? 2, because 750 torrs. So I'm going to round this to 97 grams per mole. Yay, we found the molar mass. Are we done? No, now we have to try to determine if the empirical formula and the molecular formula are exactly the same. So what I'm going to do is I'm going to find what the molar mass is of CHCl. So carbon is 12.01. Hydrogen is 1.01. Chlorine is 35.45. And it's 1 to 1, so we just have to add all of those together. So we do 12.01 plus 1.01 plus 30. We get 48.47. So it's basically doubled. We can go ahead and we could do the math just to make sure. We could take 97, we could divide it by 48.47. So in the calculator, technically, we are going to get 2.001. So it's a factor of 2. So what is our molecular formula? It's CHCl times 2. So our molecular formula is going to be C2H2Cl2. So just because we're done with molecular and empirical formulas, they might rear their ugly heads again. But this was way better than stoichiometry, right? Way easier than limiting and factors. That whole density, that formula is going to give us a little bit of trouble, I think. Just make sure you're checking your units. Make sure they cancel out. Tomorrow we're going to do some practice on the back, so don't worry about doing that for homework. We're going to do it in class tomorrow so that I can help you guys if you need it. Yes, the density equation.
Like, I
Let me
followed
turn this
it
off.
Yeah.